Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and material subject. Already three sessions are completed. In previous sessions, have discussed about stresses, strains, and what is the relation between these stress and strain and elastic constants we have seen. Now, in this today's topic, I want to discuss about stresses in composite bars. Lecture number 4. So, course outcome at the end of the course, the student should be able to explain the concepts of stress strain, material constitutional relationship, and then strain energy induced in a linear, elastic, homogeneous, and isotropic material subjected to forces. So, at the end of the topic, the student can able to answer all these concepts. CO1, the stress strain and elastic constants. What is the relation between stress strain and stress SN stress strain curve? This is already about stresses and some relationship also we have seen. So, in stresses in composite bars, in previous topics we have seen stress in a single bar, uniform bar. Suppose, so one, this is one bar subjected to tensile stress. This is steel material. Example. So, whenever this bar is subjected to load, so how do we calculate stress? Stress is equal to load per area. As per stress definitions, we can calculate stress. So how much deformed? So deformation in this bar you can calculate by using strain delta L by L. Relation between these two we have seen in Hooke's law. We have studied about Hooke's law. The Hooke's law states that the stress is directly proportional to strain. And stress is equal to, you can write E epsilon. So like this, you can write in subjected to uniform single bar. Now come to this composite bars. A composite bar may be defined as a bar made up of two or more different materials. The composite means combination of two bars. Material copper, any material to copper or steel, two or more different materials joined together in such a manner that the system extends or contracts as one unit. Equally, when subjected to tension or compression, see, whenever two materials are joined together and whenever these two are subjected to tensile or compressive load, it may be extends or contracts as a one unit. This is one material and another material. Suppose example, you see steel and copper. These two are subjected to tensile. It will extend simultaneously and contract also equal. So how do we calculate the stresses in this type of composite bars? That is today's topic. So in case of composite bars, the following point should be kept in view. The extension or contraction of the bar being equal, the strain, that is deformation per unit length, is also equal. The total external load on the bar is equal to the sum of the loads carried by different materials. So the total external load on the bar equal to the sum of the loads carried by the different materials. Suppose two materials are carrying loads, so the total load is P, so you can write P1 plus P2. This is total load. Total load is equal to the sum of the all loads. Suppose in three composite bars are there. Suppose P1 plus P2 plus P3. So this is total load. Some of the loads carried by different materials. Aluminum, copper, steel, like that. So the strain deformation per unit length is also equal. The strain also equal. So these are the main concept of stresses in composite bars. See, first you consider a composite bar made up of two different materials. So as shown in figure, in this figure, two different materials. The first one is different material 1 and the second material 2. Two different cross sections here, hatching part also shown in this figure. So the length of the bar is equal, and the load also applied subjected to P load. So as per basic concept, whatever load acting on two different materials, that is total load. Total load. The summation of load means P1 plus P2. So these two gives total load, equal load. So let P1 load carried by bar 1, and A1 cross sectional area of bar A1. So that is A1. So bar 1 cross sectional area A1, bar 2 cross sectional area A2. What is the load carried by the bar 1? P1. Sigma 1 is stress produced in bar. So what is the stress produced in bar 1? And E1, Young's modulus of bar 1. So you know the Young's modulus is equal to stress upon epsilon. As per Hooke's law, stress is directly proportional to strain. So like this, you can represent. So the P2, A2, sigma 2 and E2 corresponding values of bar 2. The total load on the composite bar P, the length of the composite bar L, delta L is elongation of the composite bar. So now need to calculate individual stresses in the bar whenever this composite bar subjected to load. See here, first calculate stress sigma 1. The sigma 1, what is the formula? Load for area. This is stress in bar 1. Similarly, stress in bar 2, P2 by A2. This is second one. Load carried, second P2 by A2. So already P2, A2 are corresponding values of bar 2 and sigma 1 stress induced of bar 1, you know. So now, you don't know the individual load, the P1, what is the load corresponding to the one first material. And this one is second material. But you know the total load, that is, we know total load is equal to the summation of two loads, that is P is equal to P1 plus P2. But how do you calculate the P1 and the P2? Need to calculate P1 and P2. So before going to calculate this one, so find out stresses. Strain. Strain 1 is equal to, as per Hooke's law, sigma is equal to Young's modulus into strain. So now you can calculate sigma 1 by E1. And strain 2, sigma 2 by E2. So, as per the basic concept of composite bar, so whatever load, the component subjected to some load, that is algebraic sum of the individual bars. Strain is the total elongation is equal. So as per definite concept, see in this, the extension or contraction of the bar being equal, that is strain, deformation per unit length is also equal. So that you can write delta sigma epsilon 1 is equal to epsilon 2. That is sigma 1 by E1 is equal to sigma 2 by E2. Clear? So now the elongation delta L is equal to PL by AE. Already we have studied in stresses. So total load here and the length of the bar and the cross-sectional area and Young's modulus. But first corresponding to the delta first bar delta L1, what is the elongation in L1 is P1 by A1 T. Delta L2 P2 by A1 into E. So these both are equal. Delta L1 is equal to delta L2. So now write down this P1 by A1 E1 is equal to P2 by A2 E2. So the total load is equal to P1 plus P2. So now you can write the P1 value in terms of P2. You can find the P2. So we will see in this. In this, P is equal to P1 plus P2. But here, right, from this equation, P2 or P1 is equal to P2 by, so first write down this equation, P1 A2 E2 is equal to P2 A1 E1. So P1 is equal to P2 A1 E1 by A2 E2. So now substitute this value in this equation. So P is equal to P1 P2 A1 E1 divided by A2 E2 plus P2. So take common here, P2 is equal to 1 plus A1 E1 by A2 E2. So now P2 is equal to P by 1 plus A1 E1 and A2 E2. So calculate P1. P1 is equal to, P2 A1 E1 by A2 E2. Now substitute this P2 value in this, you will get P1. So according to the basic concept of stresses in composite bar, delta L1 is equal to delta L2. So by using this relation, PL by AE is equal to PL2 by A2 E2. So we have calculated this P1 and P2. But sigma 1 by E1 is equal to sigma 2 by E2. So this is equal to sigma strain in first bar by strain in second bar. So here sigma 1 E2 is equal to E1 sigma 2. Now you can calculate sigma 1 is equal to E1 by E2 to sigma 2. So sigma 1 by sigma 2 is equal to E1 by E2. So the stresses bar 1 and bar 2 is equal to E1 by E2. So like this, you can calculate individual stresses and then strains in the composite bars. So now we will see one problem on this composite bars. See in this, a bar 3 meter long is made of two bars. The given length is 3 meter. One of copper having 10 to the power of 5 giganewton per meter square. And the other steel having the Young's modulus or modular velocity 210 giganewton per meter square. So each bar is 25 mm broad and 12.5 mm thick. So the given bar 25 mm broad and thickness 12.5 mm. This compound bar is stretched by a load of 50 kilonewtons. The load is load acting, that is P is equal to 50 kilonewtons. What he has asked? The finding increase in length of the compound bar and the stress produced in the steel and copper. The length of the copper as well as of the steel bar is 3 meter each. So the length of the copper as well as of steel bar is 3 meters each. The length is 3 meter. So already given here the bar is 3 meter, the combined bar. So now need to calculate increase in length of the compound bar. How much increase? Delta L. So see here the composite bars, different two materials given. One is copper, another one is steel. Here this bar is subjected to 50 kilonewtons. So length of copper given data and length of steel 3 meters. So convert into mm, that is 3000 mm length. The length of the bar, that is L1 and L2. So here Young's modulus given and then Young's modulus steel also given value. So convert into kilonewton per mm square. Meter square convert into mm square giganewton to mm. So the B is equal to 25 mm width of the bar and thickness is 12.5 mm. The length of the bar suppose like this, the bar So this length of the bar is L, and then width is B, and height or thickness, that is T. Load is 50 kilonewtons. So increase in length of the compound bar, let delta L increase in length of the compound bar. The compound bar shown in figure, but you know that the cross-sectional area of the each bar, so the each bar cross-sectional area, the copper bar is equal to B into T, steel bar B into T, width and thickness. Breadth and thickness B into T. Rectangular bar, the area is P by T. So load shared by the copper bar. So calculate this area B into T, B 25 and 12.5 given, that is T 12.5 mm square. Now use this previous relation, the composite bars, whatever we have discussed in previous slides. The copper load, that is equal to total load into A1 E1 by A2 E2 plus A2 A1 E1 plus A2 E2. P is equal to EC by Young's modulus by EC plus ES. So in this already we have seen in theory part. This one P1 is equal to P2 A2, P1 P2 is equal to A1 E1 by P2 E2, and P1 1 plus P2 is equal to P by 1 plus A1 E1 by A2 E2. So simplify this one and you will get this equation. Now substitute the given values. The total load is 50 and copper 10^5 plus 210. You will get 16.67 kilo. So you know total load P is equal to PC plus PS. If you calculate the PC value as 16.67, then substitute the PS is equal to P minus PC. Sorry. The total load shared by the composite bar 50 kilonewtons, and C the P copper load is 16.67 already calculated in this above step. Substitute, you will get 33.33 kilonewtons. So the elongation of both the bars is equal. So delta L is equal to delta L1 and delta L2. PL by AE, P1L by A1 E1 is equal to P2L2 by A2 E2. So you will get substitute all values in this. You will get delta L. Stress produced in the steel and copper bar. We know that stress produced in the steel bar is equal to sigma stress in a steel bar is equal to ES by EC into sigma C. So already we have seen in a previous slide, we have discussed about the relations sigma 1 by sigma 2 is equal to E1 by E2. So we have seen here in the previous slide, sigma 1 by sigma 2 is equal to E1 by E2. So apply this condition, this formula for this problem, EC by ES by EC into sigma C. So the value is already, substitute. We will get 2, approximately 2 sigma C. So the total load is P is equal to load in steel bar plus load in copper. So now add these two loads. 50 is equal to 2 sigma C multiply with 312.5 plus sigma C into 312.5. We will get the load of copper material. Sigma C is equal to 53 Newton per mm square. So load stress will get, that is 53 megapascal. 1 megapascal is equal to 1 into 10 to the power of 5 Newton per meter square. In terms of mm square, 1 megapascal is equal to 10 to the power of 6 Newton per mm square. So that you can write like this, sigma C in terms of megapascal, and stress in the steel bar is equal to 2 multiply with sigma C. In terms of megapascal. In our problem, what he has asked, find the increase in length of the compound bar, delta L1, produced in the steel and copper. The length of the copper as well as of steel bar is 3 meters given. So that here calculated the elongation of the both the bars are equal, that is delta L. We got 1.52 mm. Similarly, the stresses produced in the steel and copper bar, we have calculated. So next one is stresses due to change in temperature. Those stresses are called thermal stresses. The thermal stresses in composite bars, we have seen in previous slides, whenever the composite bar is subjected to tensile load or compressive load, the both materials are will elongation or contracts equally. The strain also equal. But in this case of, if any temperature is present, so temperature subjected to some heat, what will happen? So definitely there are thermal stresses. So due to these thermal stresses, sometimes the contracts are elongated in addition to the axial load. So that those stresses, how do you calculate? So whenever there is some increase or decrease in the temperature of body, So what will happen? It causes the body to expand or contract. So little consultation will show that if the body is allowed to expand or contract freely with the rise or fall of the temperature, no stresses are induced in the body. So little consultation will show that if the body is allowed to expand with the rise or fall of the temperature, there is no stresses induced in the body. But if the deformation of the body is prevented, whenever you prevented, suppose body is having like this length L, you are subjected to load and also giving thermal load, you keep on increasing the stresses. So that is keep on increasing the heat. There is no stresses. It will increase like this. But if you want to try the deformation of the body's prevent, some stresses are induced in the body. Such type of stresses are called as thermal stresses. So whenever prevented these stresses, so then there is a some stresses known as thermal stresses. How do you calculate? So let L original length of the body. Just a small t rise or fall of temperature. And alpha coefficient of thermal expansion, that is increase or decrease in length. So delta L is equal to increase or decrease in length is equal to L in L multiplied with alpha into T. So the coefficient of expansion given alpha, increase or decrease in length, the original length of the body L, and the rise or fall of the temperature also given. So if the ends of the body are fixed to rigid supports, ends of the body, suppose like this, end is closed, both ends are closed. So length is L. So that its expansion is prevented, then compressive strain induced in the body. The compressive strain, how do you calculate the compressive strain? By using this equation. Compressive strain delta L by L. Delta L by L is equal to, in place of delta L, L into alpha T by L. So thermal stresses are, yes, sigma thermal stress. So here L get cancelled, you will get alpha T. The strain is equal to alpha T. So as per Hooke's law, as per Hooke's law, stress is equal to E to epsilon. So strain is equal to stress by E. So you can write stress is equal to epsilon into E. Epsilon into E. Similarly here, apply for thermal stresses. Here stresses are thermal stresses due to heat contraction. So that is TH thermal is equal to, so epsilon, that is strain in copper. A strain in copper. Why here here the material, sorry, here only single subject we have taken, single bar. So here strain in compressive strain is equal to compressive strain change in length by original length. So the change in length is equal to L alpha T. Why? Because here coefficient of heat, the coefficient of thermal expansion will be added. So now you can write this equation. You can write the thermal stresses sigma is equal to zeta compressive strain multiplied with E. So strain in the compressive strain is equal to, calculated in above equation, that is alpha T multiply with epsilon, sorry, E, modulus of velocity or Young's modulus. Suppose in the case of the composite bar, whenever the composite bar subjected to this type of stresses, thermal stresses, how do you write this equation? So we can write this equation sigma 1, that is in first material, thermal stresses Th1 is equal to alpha 1, T1 and E1. Similarly, thermal stresses in second case alpha 2, T2, E2. So you can write this equation as a previous composite bar equation. Sigma 1, it is thermal stress 1 by upon sigma 2 thermal stress, sigma 2 thermal stresses, that is sigma 1 by sigma 2 is equal to alpha 1 T1 E1 by alpha 2 T2 E2. So that the coefficient of thermal expansion vary with the material. So that's why need to take alpha 1 and alpha 2. And temperature, you are not heating constant same temperature. Suppose any change in temperature is there, And Young's modulus also vary with the material, modulus of velocity, E1 by E2. So here delta L in previous composite bars, delta L1, that is delta L is equal to PL by AE. So here instead of this P by A, you can write delta L is equal to strain multiply with L. Strain multiply with L. So in this case, thermal stress. Why? Because the P by A is stress upon E is equal to strain. Strain multiply with L. Sorry, multiply with L. So it gives a change in length due to temperature. So in this also need to calculate thermal stresses, how much thermal stresses produced due to prevention of it expansion or contraction. Whenever these two rigid supports, these two bars or one body is fixed to rigid support, it may be single or different. So next one, these are the references I have taken for this topic, composite bars and thermal stresses. What we have learned, so once again we'll see. So in this session, so now tell me the CO1 outcome the student can able to answer or not. So the students can be able to answer the concept of stress strain and material constant relationships. So whenever this the elastic or homogeneous and isotropic material subjected to forces. So we have seen stresses in composites, and in this we have learned the total external load calculation, and then extension or contraction of the bar being equal, the strain deformation per unit length also equal. That this concept also we have studied in this composite bars. So we have taken example for these two composite bars. In this, different stresses are there. In bar 1, stress produced is different, and bar 2 is different. Similarly, the Young's modulus also depends upon the material. So here Young's modulus a bar given, and E2 corresponding values of bar 2, and load carried also different. So in this case, so how do we calculate the stresses we have studied? Sigma 1 and sigma 2 and total load. So and the strains also we have studied, and then total load calculation, and then stresses, individual stresses in the bars. Sigma 1, what is the individual stress produced by this composite bar? Sigma 1 by sigma 2. and then E1 by E2. Similarly, strain. Strain is equal to sigma 1 by sigma 2. So already we have solved one problem. In this, we have calculated the increase in the length of the compound bar and the stress produced in the steel and copper. So length of the copper also we have calculated, like given. So given data and how to calculate this type of problems we have learned. So increase in the length of the compound bar given. So here total load shared by the steel bar and copper bar individually we have calculated, and then elongation also we have calculated. So finally the stress produced in steel and copper we have determined. So next we have discussed about stresses due to change in temperature. So what do you mean by thermal stresses? So thermal stresses means whenever the two whenever the component is subjected to temperature decrease or increase in temperature of a body, sometimes it will contract or expand. If you are giving keep on heat, it will expand. No stresses are induced in the body. Whenever you have prevented, the deformation of the body will be stopped. These type of stresses are called thermal stresses. These stresses in stresses due to change in temperature, delta L, L alpha T, you have seen, and also you have calculated thermal stresses, thermal stress 1 and thermal stress 2. When the composite was subjected to this temperature. So in next sessions, in coming sessions, we will see the problem solving on these topics. So these are the references I have taken. As Ramamurthu, Strength of Materials. The title of the book is Strength of Materials. Author name is Ramamurthu. The publishers are Dhanpati Rai Publisher. Similarly, R.K. Rajput. Strength of Materials title is H. Chand and Co. New Delhi Publications. So next, R.K. Bansal. A textbook of Strength of Materials. Title is Textbook of Strength of Material, Lakshmi Publications, and R.S. Kurmi and Gupta. The title of the book is Strength of Materials, H. Chand and Co. New Delhi, the first edition in 2013. So these are the references I have taken for this preparation of PPT. So you can refer any textbook and take any one for other clarification and solve the problems. Whatever you have discussed so far. So need to calculate the problems on theory point. So in next sessions, we will see the detailed problem solving section. All these problems. So that is problems related to stresses, problems related to strains, and problems related to elastic constant relationships, and the problem related to the composite bars, and thermal stresses. So we will discuss. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.